Hi everyone, today we have Kevin Yale as our speaker. He's a software engineer at Google and a part-time student in Columbia University. Today he's going to talk about his work limits of pre-processing for a single server PIR. Let's welcome him.
All right, thanks for that introduction. I'll be talking about some lower bounds for single server PIR. This is a joint work with Pino Persiano, and all right, let's get started here. A couple things before I begin. First of all, at any point in time during the talk, please ask questions. I'm happy to answer any questions to clarify during the talk. Second of all, I'm not sure if anyone noticed, I've been feeling under the weather the last couple of days, so my voice is a little raspy. I have redness around my nose, so I'll be keeping this a little shorter than usual. So forgive me if my voice is a little off. All right, let's get started. So I'm going to assume no prior knowledge in this talk, so let's start from the basic of what is private information retrieval, or affectionately known as PIR for short. PIR essentially is a very, very simple problem. You sort of have two parties. So let's say a client on the left and a server on the right. And the server simply holds n array elements, let's say. They can be blocks, array elements, but let's say n, number 1 to n. The whole goal is for the client, when it gets an index I, to simply do some sort of interaction with the server in such a way that it can retrieve the if block. So this sounds very, very easy, right? Like, if there's no privacy, this is straightforward. So the real interesting problem here is typically when essentially what we want to do is keep this private. What we want to do is essentially say, look, we want to make sure that the index, whatever index I that I requested, remains hidden from the server that holds all the data. So, without privacy, this is really, really easy. It's simply an array access. As soon as you add privacy, it becomes a really, really hard problem. So in fact, there was a work in 2004 by Beimel and Malkin that essentially showed that any secure PIR construction, so even in the multi-server setting where one server is adversarial, but many, many servers are not even adversarial, you don't even need to hide their index from them. They showed that these constructions require linear computation. In other words, you sort of have to scan the entire database during query time. So an example, or like the simplest example I like to give of why this is true is consider your favorite, any private information retrieval scheme that you think would be sublinear. For example, here, you have n blocks, and for example, you just don't touch the second block. B2 is not touched. So let's say B2 is not touched, and what can the server see? Well, the server immediately can see that the requested index isn't 2. Right? So in a sense, this isn't surprising, although formally to prove it is slightly a little more challenging. But the fact that if you want to keep the index I private while still being able to get the if block, requiring linear computation isn't surprising. But of course, it's very slow, and it's in many places practically or computationally infeasible. So this leads to the idea of what's known as private information retrieval, or PIR with preprocessing. So to try to get around this sort of linear bottleneck, what you can instead do is sort of have a pre-processing stage where the client or user is going to do some work with the server, but it doesn't know what the index is ahead of time. So it doesn't know what it's querying. So for example, what can happen here is maybe the client and the server work together in the pre-processing stage to compute some hint. And this hint is supposed to be independent of whatever is going to be queried. So this index I, it's completely independent. And the hope is when you have query time, so when the user gets this index I, it wants to query, it can now leverage the hint in some way to make queries faster. And ideally, from a theoretical perspective, we want to make these queries sublinear in the server computation time to get around this Beimel-Malkin bottleneck. So there's actually, so what are the complexity measures we usually care about? So the two measures that we're going to be caring about the most in this talk are essentially the hint size. So what I'm going to say is we're going to use the letter R to represent how many bits the hint stored by the hints. And then the other one is T, the computational time. And in particular, what we care about is how much time the server spends during query time. So these are two complexity measures, the ones that we're going to prove our lower bounds based on. There are other ones you can think of. For example, communication is a very big complexity measure, typically in PIR. The problem is, I don't know if any of you guys have worked on this before, but lower bounds for communication in PIR are really, really hard to do, and we don't have any techniques to do so. So that remains an open question. And that's why we don't consider it in this talk. And instead, we're only going to care about hint size and computational time. Okay, so it turns out that while I describe pure preprocessing, there's actually two versions of this. The first one is what we like to call private preprocessing. So what does it mean by private? In a sense, the private means that the hint is private only to the user or the client. In a sense, the adversarial server will not be able to see the hint. So what happens is during the preprocessing stage, maybe somehow the user and the server are able to interact in such a way that only the hint is given to the client. So this has been studied in a variety of different ways, actually. So it's been called like public, or I guess it's called private key. I don't know why I said public key, but private key doubly efficient PIR, private stateful information retrieval, and more recently, offline online PIR. But the cool thing about sort of this sort of primitive is that type bounds are known already for the hint size and the time. So in particular, ignoring log factors, it's well known that that t times r, sort of the time times the size of the hint, their product must be linear. So there's another version of this, which is called public preprocessing. So here,
can I ask a question for the previous slide?
Yeah.
So when you say tight, do you mean up to polylog factors, or up to, like, I guess all of these schemes have some extra factor, right? Like maybe polylog or something.
Yeah, actually, so that's true. Actually, it turns out I think they're like, it depends on what error probability you care about. So like, let's say you do negligible error probability. I actually believe that it's only off by like even a log factor, because here we're only talking about time, right? We're not talking about sort of the size of the data that we're sending across to. But yes, there is a log factor that's sort of lost in there as well. You are correct. Any more questions? Is this model about computational or information theoretic privacy for the user's index? So we're going to consider a single server peer here, so everything is computational. Information theoretic, single server peer is like you just have to send everything. So throughout everything, I'm going to talk about computational security. All right, any other questions? All right, I'll move forward then. So the other version of this is, and the one we'll be focusing on this paper specifically, is public preprocessing. So here you can imagine the hint is publicly advertised to all parties. So in other words, both the client and the server have access to this hint. So, okay, so it turns out that public preprocessing is a much harder problem than private preprocessing. Again, this is not very surprising because of, if you have a public hint that the server sees, you actually have no hidden information from the server essentially about the database. And the best construction ends up being something that's like pretty theoretical and pretty hard. So essentially, to achieve any sublinear sort of time at this point, the best constructions still require essentially polynomial sized hits. So it's like n to the order of 1, where this constant is pretty large, and it depends on sort of what privacy and correctness that you want essentially, but it's pretty large. On the other hand, the best lower bound remains exactly the same as private preprocessing of t times r equals mega n, essentially. And so there's a pretty large gap here, in fact. Right?
Hold on, I have a question about when you say the polynomial size hints, do you mean more like square root n, not like n squared?
No, it's like n to the 100. Think n to the 100, n to the 1,000.
Oh, so do you mean like the hint is start on the server side, not on the client side in this case?
Yeah,
because
you can think of it as it's like a public bulletin board. So it can be stored by the server, it can be stored by the client, just stored somewhere publicly.
I see. So because if the client has to start this, then the client can just start the whole database itself, right?
Exactly, yeah. Yes, that's right.
So it just needs to be started on the server side.
Yeah, exactly. It's stored on the server side, or you can, like think of it like a public bulletin board, essentially. Just think of it like a public bulletin board.
Okay.
Or like a public key, yeah. But yeah, you're right that in a sense, it doesn't make sense for the client to hold it, because otherwise the client can just store the whole database, right? Good question. All right, so this is sort of a pretty open problem in the sense that the upper bound is far away from our lower bound. So, and this is the work that it's essentially the big problem that we're going to try to target in this paper. All right, so okay, before I move on, any other questions about the public preprocessing model? All right.
So I guess when you say T times R, in this case, I guess I don't understand the exact statement. Like, is T here also counting the server storage? Because it seems like when you are saying hint, now it's talking about the server storage.
Okay, so yeah, okay, so you're asking precisely what is R, right?
Oh,
And
what
essentially
is
here, so T is essentially the time of the server during query time, during online query
okay,
time.
then I'm asking what is R?
So R essentially you can think of as the redundancy. So in public preprocessing, you can think of what is it that you store that the server, let's see, okay, fine. Let's just say, to make it simplest, what is a server's redundancy? How many extra bits does the server store on top of the original data bits? Does that make sense?
Yeah, it makes sense. I guess the definition of the R is different from the private case, because the private case, I guess that bound is about, is it like the communication in the offline phase or something?
No, it's the client storage. Essentially, in the private case, the R is how much the client stores. Essentially.
Mm-hmm.
So, I guess this is sort of a bad model here. This picture is a little off. You should really think of the hint not being stored by the client, but rather in like a public bulletin board or just stored by the server, essentially. And in the private preprocessing model, this is actually correct in the sense that the client is the one that actually stores the hints. So you don't think of R beyond linear, essentially, obviously. You think of R like sublinear in that regime. Does that make sense?
Yeah.
Okay. All right, I guess I'll move forward then. So let's go to the main results of our paper. So, so this paper is pretty. It's like essentially we're proving lower bounds. So it's gonna be a lot of information theoretic techniques and sort of basic ideas, like basic information theoretic ideas. But the main result we essentially prove is that for any computationally secure single server peer that has R bits of preprocessed hints and T entries probed during query time, it must be that if R is greater than omega log n, the product is equal to omega n log n. And if the hint is less than log n size, then it requires still linear time. So this makes sense. Like, to parse this quickly, I want to say that obviously one can always construct a peer scheme that ignores the hint. So essentially that's why we need this if statement essentially. So only when the hint is large enough does our lower bound kick in, because if the hint is so small or even just 1 bit, you can always apply your favorite single server peer scheme that requires linear time. And our lower bound holds even when the peer scheme errors are probably at most 1 over n squared, essentially. And for computational security, in fact, we even prove it for advantage that's even polynomial, which is much larger than what we can typically consider as an advantage.
Sorry, when you say computationally secure, what do you mean exactly?
Right. So what I essentially mean is that I'm considering a peer scheme that's secure against any probabilistic polynomial time Turing machine or algorithm, essentially. Right. So essentially, in terms of lower bounds, what does this mean is I'm going to have to construct an adversary that's efficient, that's polynomial time and efficient. But since it's a lower bound, our results obviously apply directly to information theoretic schemes automatically.
Okay, thanks.
All right, so one of you guys must be asking, which is something I asked as well. So okay, so the previous lower bound is T times R is equal to omega n, and you add an extra log n factor. Great, it's not really solving the problem, and I actually agree with you in a sense that we're very far from resolving the actual problem. But I'm going to tell you that it turns out that adding this log n factor really wasn't that easy, in the sense that this is the first sort of improvement on this lower bound in the last 20 years. So in fact, my advisor, Tal Malkin, during her PhD, actually wrote the first paper that proved the lower bound of T times R equals omega n. So this has been like 20 years or 22 years now, actually, before the first improvement of it. Which I guess, you can always argue that maybe no one looked at the problem, which is probably true as well. But the second one, which was much more interesting to me, was that it turns out, based on the current techniques, this is the highest lower bound that we could ever attain to achieve without breaking much more bigger open problems. So in particular, it turns out that improving our lower bound, even by any asymptotic factor, would immediately imply higher branching program lower bounds. And this in particular has been an open problem in the TCS community for like 3 decades now. So in particular, I guess I'm trying.
I guess I would just say, what is a higher branching program lower bound?
Well, I think it's log n. I think you can transform essentially. If you want to look at the actual sort of reduction of how it's done, it's an original paper by Beimel and Malcolm in their journal version, where they essentially show that you can reduce PIR. You can actually construct a PIR scheme using like sort of okay, I forget which way it exactly goes, but you can reduce it to branching programs. And I think the highest branching programs are log n. I mean, there's a trade-off, right? Because branching programs, it depends on their size. So I don't know the exact bound, but essentially, if you plug in R lower bound directly into that reduction, you get exactly what matches the highest branching program lower bounds. Does that make sense? Okay, I guess I'll continue. So anyways, this is, I guess what I was trying to say, that even though it's only a log n factor, it turns out that it's actually quite difficult to achieve, and we had some very cool new ideas to get there along. All right, so before I prove the lower bound, it's very important that I describe to you the model of which we're proving that lower bound. So what we're going to use is essentially what's called the standard PIR model that has sort of 2 features. The first is actually a negative, while the second is a positive. So the first is that we require the database to be stored without any encoding. So what does that mean? And essentially, this picture describes it, where essentially we expect the server to store the n blocks as is. So that, we're going to assume that the block is, stored exactly as is, and you're not encoding it. For example, you're not using your favorite error correcting code, your favorite local code. We're really requiring you to store the database exactly as is. And the second one is essentially that we're going to sort of use ideas from the cell probe model, where we essentially say that the only cost that we're sort of charging in this model is probing database entries. So for example, every time the client probes any specific entry in the database, we're going to charge you 1 unit of cost. But that means everything else is free. So for example, generating randomness, accessing the hints, and your favorite computation can be free of charge. So for example, in this model, you can solve your favorite P versus NP problem. Like you can solve your favorite NP problem. You can even solve the halting problem if you want. It's going to be free of charge. And all we really care about is charging for accesses to the database. So this makes it sort of the lower bound stronger in a sense, because of it only charges sort of accesses. All right, so some discussion about this. Let's see. There's the land changer. Okay, so let me just do it. This is actually exactly the discussion. So what is typically called sort of like the model that sort of allows sort of arbitrary encoding is what's typically called the cell probe model. So this would allow the server to sort of encode anything it wants. So the problem with this is, first of all, we don't have techniques. So the highest cell probe lower bounds in dynamic data structures is polylogarithmic, and really it's just log squared, not even log squared. It's log squared over some log factors. And this was by Larson in 2012. So it turns out that the techniques are far too weak to prove anything that we can hope at this point. And it's really an open problem to prove any cell probe lower bounds that are super polylog, essentially. The second sort of limitation, which is actually much more, I think, interesting for me, was that proving lower bounds similar to ours in the cell probe model, where you have arbitrary encoding, is actually one way for you to rule out the existence of certain types of obfuscation. So in fact, Boyle, Ashai, Pass, and Reuters in 2017 at TCC, they showed that given the existence of obfuscation, a certain type of obfuscation, you can actually beat our lower bounds if you do server encoding. So in a sense, proving higher lower bounds in our model, in this model, would be able to rule out obfuscation, which is very scary based on recent work that shows that, that gives pretty plausible sort of construction for obfuscation. So that's why we don't consider it.
I don't understand this statement. What do you mean proving what kind of lower bound will rule out the obfuscation? And what kind of obfuscation will it rule out? I don't understand the statement.
Okay, so let's see. I don't know. I'm not very familiar with obfuscation, but let's do this carefully. If you prove not even our lower bound, but the original lower bound of t times r equals omega n in the cell probe model with arbitrary server encoding, that would mean that the Boyle, Ashai, Pass, and Reuters construction doesn't exist. And the assumption that they use there is that they require obfuscation. I don't remember which type of obfuscation. I don't really know, but so it would be one way to rule it out essentially. And I recall last time I talked to, I think, Yuval, the obfuscation they use is not a very strong version. So it's actually, it would be pretty hard to prove this kind of lower bound.
Well,
And there's like many.
They have a couple schemes in their paper, right? So one uses VBB obfuscation and the other one uses some kind of oblivious LDC. Which one are you ruling
No,
out?
not the oblivious LDC. The oblivious LDC one is not, it's not technically public preprocessing, that's private preprocessing because they store the permutation. I think it's the VBBIO one, essentially, is the one that would cause it.
I think there's a follow-up discussion in the chat.
I see. If they assumed that some complications will not by this. Yeah, essentially essentially, long story short, I think that it'd be like proving lower bounds in this model would be very difficult, essentially, because of, you know, it's a pretty dangerous game to try to rule out obfuscation, especially that we have some of them that seem to exist now in their well-studied assumptions. So that's correct. Which is the reason why we don't study in this, use this model in this paper. All right, does that answer your question, George? Okay, great. And the second interesting feature is that it turns out that this standard PIR model does model all known constructions. Turns out that the most efficient known constructions actually store the database without encoding on the server side. So, you know, that's good news. It actually is a reason for us to study this model, right? All right. Okay, so are there any other questions about the model before I move on to the technical overview? All right, I'll move on then. So this is not so simple proof, but I'm going to break it down into 4 steps that are hopefully somewhat simpler. So for any lower bound, the first thing you always have to do is construct the hard distribution. You know, what is the hard distribution for which I'm going to prove my lower bound? So the one we end up choosing is, let's suppose you have an R bit hint. So R is an arbitrary parameter here. What we do is we take the database of n entries and split it up into R groups, each of n over R size. You know, for my own sanity, let's just suppose R, R and R is divisible, and these are all real integers, but sort of what we're going to do is we're going to break it up into R groups, each of n over R size. And then what we're going to do is for each of these groups of R groups, I am going to pick one of the R locations at random and essentially encode a non-zero entry, a random non-zero entry in that location. Again, I'm gonna, even though I'm gonna represent non-zero entries as 1, really these are, you should imagine these as blocks. So they're, they're slightly larger than 1 bit. I think we need 4 bits for our proof. But really what's happening is, what I'm trying to say is you're gonna pick a random location, and in that random location, you're gonna encode a non-zero entry there, and then everything, all the R minus 1 other entries will be non-zero. And then independently, you'll do this for all R groups. And this will be our hard distribution for the database. And it turns out this is the only distribution we need because the only input is the database, really, as well as the query, but we'll talk about query later. Okay, so this seems like an arbitrary thing. Why this specific hard distribution, right? So it turns out that this hard distribution has a lot of cool facts that we'll end up using later. So let's start off by the simplest fact. Let's suppose there's no hint. And now, simply, I have this hard distribution. I don't really know what the database looks like, and all I'm going to do is try to find non-zero entries. Well, if the whole goal is just find a single non-zero entry in a group, you can easily show that finding a single non-zero entry in a group without any hint requires probing omega n over R entries on an expectation. Really, if I don't know the location, I have to really try almost all of them before I can find the non-zero entry. And whichever way I do this, it'll still end up being like this. So okay, so this is not surprising. This is, I guess, somewhat cool. All right, the second part, which is going to start giving you a little more tuition into the proof. Now let's take the natural sort of idea where, let's say we have this R bit hint, and what we're going to essentially do is spread them out equally. I know that each of these R groups are generated independently, so it's probably only fair that I use the average and give each of these groups 1 bit of hint to try to find this 1 bit entry. Well, yeah, if I have 1 bit of a hint, what can I really do with it? I can sort of reduce the search space by half, but I'm still going to require omega n over R entries of probing to even find the 1 bit, the non-zero entry in the group. And sort of this is the intuition of why this hard distribution makes sense. So the hopeful goal that we're going to end up trying to prove later is, if you do 1 probe, in expectation, you're going to find an entry with probability 1 over n over R, right? So now let's suppose linear expectation works as we would expect, then you can say that if you probe T entries, you would only find T over N over R non-zero entries. And this is the hopeful goal of our proof, and this is why we chose this specific hard distribution for any arbit hint. Okay, step one. Did that make sense at a high level? Why intuition? Not much intuition here, but why we chose this hard distribution. All right, I'll keep moving on then. Okay, so step two is now we actually have to do that hopeful or intuition and goal, right? We need to upper bound the number of discovered non-zero entries for query sequences. We actually need to prove that lemma. So let's go about doing that. And this is actually one of the more difficult parts of the proof. So before I had assumed that, okay, you know, this hint is used beautifully. I want to use 1 bit per group, and you know, life is good. I can prove everything I want. Yeah, but you know, data structures don't work like that. There might be some stupid data structure that says, okay, I'm going to use the whole arbit hint for this group. And now my whole argument falls apart in a sense, right? Maybe it does, maybe it doesn't. But you know, what I'm trying to say is you can't assume anything about how the hint is being used. It could be done in some random arbitrary way that's like, I can't predict. So I can't assume that obviously they're going to use 1 bit per of the hint for each group. Okay, but it turns out that still, let's think about this a little more carefully. What can you really do with this arbit hint? It's not that much information, right? So for example, let's think about it. You know, if you have an arbit hint, and I have, you know, each of these groups, which I'm embedding a non-zero entry in one of the sort of N over R locations. So encoding a single non-zero entry requires log N over R bits. So an R bit hint can encode the locations of R divided by log N over R, sort of non-zero entries. All right, so this sort of you know, breaks our intuition a little bit, because of what you can now do is that a query that probes T entries, I can read the hint, get exactly what I encoded in there, plus whatever I expected before. I can still use the same technique as I did before to try to find the remaining entries, right? So, okay, it doesn't work exactly, but let's think about how we could actually get around this. So it turns out the following insight is actually key. Let's say you have multiple queries, and you know this R bit hint was being adversarial and just trying to, you know, it really encoded like the locations of entries. Well, you know, this hint will only let you discover the exact same entries over and over again. It's not like if I query 100 times, I'm going to get 100 times that, right? And this is the real intuition, essentially. What you end up doing is, what you can essentially say is that, okay, now you have this R bit hint, but let's consider a large sequence of queries, right? Let's not just consider one, let's consider several, or you know, whatever. You know, this R bit hint can be used to get some hints for free, but if this query sequence is long enough, you really shouldn't be able to beat my lower, but you shouldn't be able to beat this bound, right? This idea, you know, for each probe, I'm only going to find 1 over N over R non-zero entries per probe. And it turns out that this is exactly how we'll end up doing it. We'll essentially show that over a large enough sequence of queries, you can't do it. You can't actually find too many queries, and that whatever our original intuition will prove is true. All right, so how we do this formally is what we have to define. We define this query sequence called maximally discovered. So what it essentially means is that what I want to do is find a query sequence that's the longest sequence, such that what happens is that each query in this sequence will discover at least omega log n entries that were previously unprobed. So what does this mean? Let's suppose you had whatever is so-called maximally discovering I-1 queries. If I want to add another query, the if query, into this sequence, it better be that they discover omega log n new non-zero entries. And when I mean new, I mean ones that were not previously probed by any of the previous I-1 queries. So, you know, what I'm showing here essentially is that maybe I color all the non-zero entries that are probed by the I-1 first queries by green. And what I want is for this if query to be able to be added to this maximal sequence, it better be that it probes essentially omega log n non-zero entries that are colored, like that are uncolored at this point. Okay, so now that we have this, what we essentially end up proving is essentially what we expect is sort of that this maximally discovering sequence for the first thing can't be too large. In fact, you know, the number of queries in this sequence has to be R over log n. And the second is that the total number of discovered non-zero entries. So, you know, even if maybe Q is the number of queries number of indices isn't very large, it's very possible that somehow one of the queries is able to find half the entries in the database. And we sort of prove that this is not the case in a sense, that you can only discover maybe 1 over 1/28 of the database. Does that make sense? Any questions on sort of this theorem because it's, I guess, a core part of our proof. All right, so let's talk about how to prove this then. So at a very high level, the proof sketch is sort of the standard data structure, sort of lower bound, where we say, okay, let's go towards a contradiction. Let's suppose this maximally discovering query sequence that contradicts the theorem exists. Then what we essentially do is we will sort of use this maximally discovering query sequence to compress the original database from the hard distribution beyond information theoretic bounds to drive a contradiction. So essentially we'll say that, look, if this Q exists, I can use this too good to be existing Q to be able to compress this database beyond the entropy of the database that was originally used to derive it. All right, so formally do this, what we end up doing is a standard compression technique where you have an encoder and a decoder. The encoder gets the database D, which is random. So there's, it's drawn randomly from the hard distribution. The encoder will send a single encoding of D that should let the decoder perfectly decode the database all the time. So if we consider this sort of compression, sort of one-way compression protocol or setting, we can invoke Shannon's source code theorem, which essentially says for any prefix-free encoding scheme that enables perfect decoding, the expected length of the encoding must be at least the entropy of its input, so the entropy of the database D. So great, we've converted our lower bound question to an upper bound question, which is what I like more. Essentially, what we're trying to do now is to algorithmically find an encoding scheme that minimizes the encoding length. And if we can minimize the encoding length using this too good to be true maximally discovered sequence, I can break Shannon's theorem and I can continue, I can prove my theorem. All right, so how do we do this? Well, turns out that once you have this sort of setup, it's not too difficult to follow. Essentially, you have this Q that's too good to be true, so let's use it, right? And what we're going to essentially do is we can encode Q in such a way that the decoder will be able to actually execute the data, execute all the queries in the query sequence identically to the encoder. And it turns out that actually this is enough to actually provide to get a contradiction and compress beyond the information theoretic bounds. But let me explain exactly how. So essentially, how do we encode Q such that the decoder has the ability to execute all the queries in Q? And it turns out you only need three things. So the first is, okay, I obviously need to give you the query indices to be able to run. The second thing it turns out is, what you're going to have is when you run this sequence of queries, you're going to get a sequence of probes. And what I'm going to do is amongst this sequence of probes, I'm going to tell you which subset of them are non-zero entries. So I'll tell you, the third unique entry you're going to probe is going to be a non-zero entry. The 25th the entry you're going to probe that's unique will be to a non-zero entry. And then finally, for each of these these subsets, I'm going to tell you exactly the contents of the probe non-zero entries. And it turns out, you have to get the perfect decoding. So everything you miss in the last step, you just encode naively. All the non-zero entries that are missing, and you will be able to encode step 3. So let's dig a little bit closer into the third step. What does the decoder have? So the decoder's view of the database looks something like this right now, right? It has a bunch of question marks everywhere. So what it's going to do is, whenever it's executing a query Q, it's going to run a bunch of probes to the database. So maybe it probes this sort of entry. And sort of what you can do is use the last two components of the encoding, the subset of probes to non-zero entries as well as the contents to be able to continue. So you can quickly tell that, hey, if this is not one of the probes that are this is not one of the probes in the subset, it's to a 0 entry. So I can act like the contents are 0 and continue. So for example, I can do this. On the other hand, maybe I probe this thing and the subset actually says, oh, the second probe is to a non-zero entry. So you look at its contents. And what I can then do is actually say, okay, I know what its contents now, so I can use it. I can act as if I actually use the real database and continue the probe. And sort of this ends up being enough for the decoder to actually be able to execute all the queries. Now, if you're asking sort of how did you win, right? Like, how is this encoding better than sort of the standard technique? There must be some way that I'm compressing beyond the information theoretic bounds to get in a contradiction. And it turns out it's just step B. So think about this carefully. For example, let's suppose an extreme case where the query only probes two entries. So usually what I have to do is, if I wanted to, without using this maximally discoverable query sequence, what I actually have to do is say, look, I have to tell you from the entire, from the entire group of n over r entries, which one of these is the one entry. But remember, we're assuming contradiction here. So we have a PIR scheme that's too good to be true, beating our lower bound. That means it doesn't probe too many entries. So in fact, this step B, where I'm describing a subset of the probes to non-zero entries, turns out to be compressing far too well beyond Shannon's sort of theorem. And essentially, this is how we derive our contradiction. Essentially, this is like the main way we're able to prove this lower bound. So I'm going to skip all the math because I didn't. It's a little annoying, but sort of I wanted to give you the idea of how we came up with this proof. Okay, any questions on step 2 before I move on? All right, I'll move on then. All right, so step 3. Now we have essentially a bound on how many discovered non-zero entries are done for these query sequences. So using this, we're going to end up constructing a very powerful PPT adversary using what's so-called the cell sampling technique. So I guess a little bit about the cell sampling technique. It ends up being the optimal technique for proving static data structure lower bounds. And to our knowledge, this is the first time the technique has been used in cryptography to construct an adversary. So I think it's actually pretty cool, but it's just sort of a side note. All right, so how do we do this? So what we're going to end up doing is start coloring cells. So we have this maximally discovering query sequence Q. So all of the non-zero entries that are probed by it, we're going to color them green. So now what happens is you have all of these non-zero entries that are essentially uncolored. They weren't probed by the maximally discovering query sequence. So we're going to take these and sort of break them up into 2 components based on what's called cell sampling. And it's sort of exactly what it says. What we're going to do is sample each cell independently probably like 1 over 100. So what ends up happening is, maybe we sample the far right one, but we don't sample the one in the middle. So what ends up happening is you get 3 different sets of cells. You get the ones discovered by Q, you get the uncolored ones that are unsampled, and you get the orange colored ones which are sampled. All right, so I said, what I've done, like, this doesn't seem to make sense. I've taken all of these non-zero entries that are not sort of probed by the maximally discovering query sequence and said, okay, I'm going to sample them with IID probability 1 over 100. Well, okay, let's use 2 facts. The first fact is, the maximally discovering Q is maximally discovering. It's the largest possible sequence. So any query following it will discover little O of log n new non-zero entries. Right? This is just by definition. And now let's think about this. Actually, this is actually pretty interesting. This is a very, very simple argument. So now let's take any query following the maximally discovering query sequence Q. It's going to only discover little O of log n new non-zero entries. So amongst these, I've sampled each of them with probability 1 over 100. So so then let's consider the events that when some query Q following the maximally discovered query sequence probes only cells that are sampled. Well, it turns out that it's, this is very simple to compute. It's 1 over 100 to the power of little O of log n, which ends up being at most 1 over poly n. So this 1 over poly n is very important because this is a good probability. This is something a PPT adversary can actually measure. And it turns out exactly that this is the key reason that we can actually do this. So to put this in pictures, what I'm trying to say essentially is you have this maximally discovering Q with all of its green sort of cells. When you have a query Q that follows it, I'm really, really looking at the instance where it only probes cells that are either colored green or orange and nothing else. And it turns out that this occurs with 1 over poly n probability. And it turns out from this idea, you can actually construct a PPT adversary that can break privacy unless it turns out that for all possible queries, that this statement holds true essentially, that whether it's this Q could be 1, 2, 3, all the way to n. For any of the n entries you query, it must be true that they sort of have this picture of not querying any of the uncolored non-zero entries with 1 over poly n probability. And sort of the main idea of how to do this essentially is just very straightforward. You just apply a turn-off bound where you essentially say, look, as an adversary, I have the public hints. I'm just going to query Q prime that's not equal to Q many, many times. And if I don't see that it has that setting with at least probability 1 over poly n, I know you're not secure essentially. So this ends up being the adversary that we use to prove our lower bound. But again, it's still not clear how I can use this adversary to complete the proof, which ends up being the final step. So before I move on, any questions about the adversary? If that makes sense. All right, I'll take silence as either I've completely lost everyone or everyone understands, or something between. All right, so now, given this adversary, how do I complete the proof? Very, very simple, right? So the idea essentially is that, let's look at this picture. Let's look at this picture. So let's say this query Q is to not, this query Q is, what is a pure query? It's saying, look, I want you to return the entry at some index, right? So in fact, this Q could be for an entry that's not colored green or orange. So it could be, for example, any query, any entry in the middle section. Well, that seems too good to be true, right? That seems impossibly good. Somehow I'm able to use only the green and orange cells and magically get everything in the database. And this is exactly how we prove, we do the final encoding scheme essentially. So going back to the proof, what happens is if you try enough times, you're able to simulate all PIR queries using only sample cells and non-zero entries discovered by any maximum discovery. So look at this picture. This queue, you can plug in 1, 2, 3, whatever you want. You can plug in any of the n entries. And I can, if I try enough times, I'm able to get the correct answer by only using the contents of the green and orange cells, which is impossible. And this is how we complete the proof. So how do we do this? So yeah, okay. I guess I'm just coloring and you're telling me that this is all you need, according to if you had this sort of a construction that's too good to be true. Yeah, so okay, I guess I just wrote down exactly what I said. So you recover the entire database using only a subset of the non-zero entries. And this would again contradict Shannon's source coding theorem. So going back to exactly this idea, we're going to do another impossible encoding scheme to prove the final result. And it turns out that once you have sort of all of these theorems, the encoding scheme becomes sort of trivial. You encode the hint. There's some technical reason you actually end up needing encoding all the locations of the non-zero entries, but not the actual contents. You encode all the sampled cells. Then you encode sort of this maximally discovering query sequence. And then what you can end up doing is letting the decoder sort of, try all the entries that it hasn't seen yet, and then just run queries. And somehow it'll eventually find some randomness that'll let you give you an answer for it by only probing sampled or previously probed cells. So for example, here, looking at this picture, what ends up happening is maybe you're doing a query for this entry, which is not green or orange. If you try enough times, you'll get this picture where it only probes the green or orange cells, but it's able to give you the correct answer. So afterwards, I am able to get this content blue essentially for free, which is impossible, right? This is still a random bit, and sort of if you do this enough times, you'll get, you can color every single of these white cells blue, and you'll be able to get the whole content of the database essentially for free. All right, so that's it. That's the entire proof. Are there any questions? Anything I can sort of clarify? It's a pretty complicated proof. It has several new ideas. To be honest, I've glossed over a lot of the tiny details. A lot of these things, these theorems are pretty imprecise because you need like probabilities, distributions, and stuff. But I hope people are able to get sort of the high-level techniques that we use of like cell sampling, of like Shannon's source coding theorem and encodings, of like being able to sort of convert a lower bound problem into an algorithmic upper bound problem, which I think is one of the cool parts of actually proving lower bounds, is that it still uses the same ideas as your upper bounds. So, are there any questions?
Yeah, I have a question. So you prove, I guess you prove the lower bound for computationally secure schemes. Did anything simplify if you just consider, say, information theoretic security, or was it just something that came out for free, I guess, from your?
No. It doesn't come out for free. For information theoretic, it's really easy to prove, I think.
Okay.
Like, I believe it's really, really easy because of so the whole difficulty of our proof essentially is that, look, we need to be able to make sure that this adversary is able to simulate this result using 1 over polynomial. So you can shortcut probably to the second and third steps essentially. For example,
was it known before for the, or was that also open even for information theoretic security, or just not interesting, or?
I don't think it was known for information theoretic either, but I don't like information theoretic single server PIR is not considered very interesting, right?
Right.
In a sense, because you have to download the whole database anyways.
I see.
So it's not exactly the most interesting, but I mean, I don't think people looked at it, let's say. I think the computational security was more interesting. Yeah.
Right, yeah, makes sense. Thanks.
I guess I have another question about the end of step 2 of the proof steps.
Okay, let's go back. Which?
Yeah, like the last slides, I guess.
Oh,
Yeah, this one.
I think
So,
this one right here.
yeah, I mean, intuitionally, I didn't get how this goes below the entropy lower bound of the compression encoding with encoding of this probes of non-zero entries, or
So okay, so exactly. So the reason this is very annoying is that Shannon's source coding theorem requires perfect decoding, right? I mean, there are probably some versions of this that you can get it with non-perfect, but I don't know, it's easier to like modify the encoding. So in a sense, what you should think of in the following way. You can think of maybe step 3 encoding half the database and step 4 encoding half the database. So step 4 will meet exactly the information theoretic bound, right? Because if you code it naively, there's a very simple way to do this. So it doesn't really matter which half we sort of encode that beats the bound, but if step 3 beats the bound while step 4 just meets it, you still actually end up beating the bound. So you should really view it as what I'm doing is I'm making sure step 3 I'm able to beat the bound for sufficiently enough a number of entries essentially.
okay.
Does that make sense?
Yeah, thank you.
All right, but that's a good question. All right, so I guess like maybe to conclude, all right, I think I went back too far, but sort of the conclusion again is that, okay, look, we're able to improve the lower bound by a log and a factor, but to get there was a long journey. Many, it's a very, very complicated proof, 4 steps. It's been an open problem for a long time. And there's a lot of cool new ideas in here that I hope people can use for other results elsewhere, essentially, for putting lower bounds elsewhere in various things. Okay. All right. Sorry.
So can your technique extend to 2 or multiple servers, or do you think there is?
No, it can't. It really can't. I'll tell you why. We thought about this for a while. It's an open question. Feel free to tackle it. But long story short, it breaks somewhere around here. I don't remember exactly. But step 3, this simple argument only applies in a single server setting. Like you need to somehow, I don't remember the exact details, but you need to somehow coordinate the sample cells across all of the servers to make it work. But somehow you really can't if you don't see all the cells. So for example, let's say you have 2 server PIR. One of them is completely empty. The adversary can't see it. Then I can't actually simulate it. So I have no clue how to do it. So in fact, our techniques only apply for a single server. So even though the result is very weak, it's even a little more embarrassing that it only applies to a single server. And that's a great open question to try to tackle. And it's one I thought about for a while, so I don't know how to do it.
Thank you.
All right, any other questions?
If you know, let's thank Kevin then. Actually, yeah, I do have a question. Sorry, now that I guess so. You got this log n factor, this extra log n factor, right? What do you think is actually like the right answer? Do you have any idea about that, or you think you're like very far away, or not necessarily?
I personally think it's very far away. I think the lower bound techniques are embarrassingly weak. I think the real lower bound is something much higher. But
do you think it's
I don't
close
have
to like the actual the construction that exists, like that requires this end to a
I don't think it's that bad. I don't think it's that bad, but I wouldn't be surprised, for example, if you can prove that T times R could be like n squared even.
I see.
I wouldn't be surprised.
I see. Yeah. Thanks.
So I guess like other things I would mention is that this lower bound, I don't know the exact connection, but I think it's very connected to like local code lower bound. So for example, this cell sampling technique I described, is exactly the best lower bound for locally decodable codes, right? And this is self-sampling are also the highest lower bounds that we can prove for static data structures, you know, in the cell probe model, which recently have been shown, and I think by Omri a couple of years ago, that showed essentially this is related. Like if you can actually get a higher lower bound for static data structures, you'll actually beat variance conjectures on like rigid matrices. So there's like this sort of where we hit sort of, you know, this bound, how high we went in terms of branching programs. It turns out that it's all related in a sense. There's all of these open problems in TCS that are like all like end up being sort of stuck at the same location. So I think it also like I believe that locally decodable codes have higher lower bounds. But if you didn't believe that, then you should probably believe that this might be the best bound you could get as well. So they're all related. Even like this, you know, super linear circuit lower bounds. That might also be something that if you believe they're super linear, like we actually know they're super linear circuits, but we just don't know what explicit. But sort of, you know, being like these are all related in a sense.
I see. Right. Yeah. Thanks.
Thank you.